Welcome back to the channel. Hope everybody's doing well, and in today's video we're going to be taking a look at some thermocouples and temperature transmitters. We've got our four cheapo calibrators lined up here that we've done a lot of other videos on previously of the different functionality. This is probably one of the last functions I've left to test with this. I probably should have done it quite a while back really, but there you go. We have our MR9270S here, and our SG-004A and our LB02 process calibrators. These can all source and measure millivolts, and they can also source and measure thermocouple in terms of degrees Celsius or degrees Fahrenheit. They can do the conversion for you from the millivolts. Our little SG-003A here, that unfortunately cannot measure millivolts and it cannot measure temperature, but it can do milliamps. So when we come to test some of our thermocouple transmitters here, temperature transmitters, we'll be able to use this to measure the milliamp output from those. Just put this little graphic up here. This is the capability of our three units. I guess the first thing that you'll see straight away is for our LB02, we've got this grey area blocked out here. For the WRE3 and WRE5 thermocouples. They are actually specialist thermocouples. They are tungsten rhenium alloy. They're used in aerospace, nuclear, and some medical industries as well. Very, very high temperature. So surprising that our SG-004A and our MR9270S do actually have that functionality, but they do. But I don't have any means of testing them. I don't have any of those. Thermocouples that I'm going to be interested in the most are going to be the K-type and the T-type. Putting those special thermocouples to one side, the first column on the table is a thermocouple type. Then you have the usable range. That's from the Omega website. That's typical for that type of thermocouple, what temperature range it will operate in. And then for each of the process calibrators, we've got the range that can transmit and measure over, the resolution and the tolerance for that measurement and sourcing. Now when you look through these, it looks like the LB02 has the best kind of ranges, and it also looks to probably have the best tolerance as well. Our SG-004A is probably the worst tolerance, and our MR9270S is probably somewhere in between. I'm not sure about the tolerance on the MR9270S. You see that it lacks anything with regard to digits, whereas the other two units do have a digit as part of their tolerance, which is typical for these digital instruments. You will also notice that our LB02, from the spec sheets, these data I've put up here is just from the spec sheets, that is the only one that can go to negative temperatures. We'll come back to that, because that's not what I found when you actually test the units out themselves. The remaining factor on this table is right down there at the very bottom in the millivolt line. We have the millivolt functionality, which you can see there. Oddly enough, our LB02 can't go negative millivolts, but it can do negative temperatures. It's probably got the best tolerance, I think. Yeah, the best tolerance. And the worst tolerance for the MR9270S, the SG-004A, probably somewhere in between. Both the SG-004A and the MR9270S can do negative millivolts. And then just at the bottom there, we talked about these tungsten rhenium thermocouples. There's a typical price there you see for per metre of thermocouple wire, £95 for the specialist ones. Against a standard K-type of £3.35 and T-type £1.63, so that's a very, very specialised thermocouple there. As I say, I'm surprised that these units have it. Just to bring up briefly this next table, this is the actual measurement capabilities that I found when I played around with these units. I put it against the specified that we saw in the previous table, but you can see in actual fact that the SG-004A and the MR9270S do have negative temperature capability. Some of the ranges they do go beyond the LB02, and some of them they don't. The really, really big flag that I found when testing these, and I'll demonstrate this later on in the video, is for the T-type thermocouple and the SG-004A. Apparently it can do 0 to 390 degrees C from the spec, but I cannot get the temperature to go below 270 degrees C for the SG-004A on that one. The MR9270S can go down to minus 270 degrees C. I suspect there's a problem with the firmware with the SG-004A, and that should also be minus 270, but for some strange reason it's not there, and it fails when trying to test one of the instruments out. But yeah, that's the basic functionality. What we'll do is we'll set up some thermocouples and we'll do some measurements with that just to show you briefly what goes on. So we've set up a couple of thermocouples here. One on the SG-004A is at ambient temperature, and we've got one sitting here in a dry well. We're set to 160 degrees C on our MR9270S here. To set this up for millivolt operation, we can go to function and input, and then go to the millivolt function there. It's set to thermocouple at the moment, so if we hit the enter on that and again, and then we can set this and set it to 110 millivolts, and then just back out of that, and we should be measuring millivolts, which you can see up there as 0.06 millivolts on there. To set up our MR9270S, we can go to the in there, and we want to go to millivolts, which is in the centre there, number 5, and there's our millivolts there. Now to get this to measure into millivolts, we need a reference table. I have here this one here from Omega. This is for the K-type, and what this does is it tells you the expected millivolts output of the thermocouple for a given temperature. What you also need to know is the ambient temperature, which is 18.2 degrees C at this moment in time. So looking at our reference table for an ambient temperature of 18 degrees C, which is what this thermocouple will be at, we should be having a voltage of 0.718 millivolts, and for 160 degrees C thermocouple we should have a voltage of 6.540 millivolts. So on our SG-004A, hopefully you can see there, it's just effectively showing 0 millivolts. So it's not reading that up at all. For our MR9270S here, we are actually reading 5.82 millivolts. So that's out of specification as well. Now, people who are used to dealing with thermocouples know what's going on here. For those that don't, a thermocouple actually has two junctions in it. We have the junction here where the probe is here. We usually call this the hot junction, and that's the temperature we're trying to measure. However, there is a second junction at the point where the thermocouple changes from its reference cable, which is all in this silver here, to the copper conductors of the instrument or the plant, whatever is going to. They usually call that cold junction temperature, and that will usually be sitting at ambient. So what our instruments are actually measuring is the voltage difference between the hot junction temperature, which for ambient should be 0.718, and the cold junction temperature, which, since that's at ambient as well, that will also be 0.78 millivolts. Therefore, the difference between that is 0, so our reading on our SG-004A is actually correct. In the same manner, we've got 5.81 millivolts on this junction here, but at this junction here we will have 0.718 millivolts, and the difference between 6.54 millivolts and 0.718 millivolts is in actual fact 5.81 millivolts, which is correct. So whenever you're measuring thermocouples in terms of millivolts, what you actually have to do is find out your ambient temperature, obtain the millivolt reading for that from the reference table, and then subtract that from the actual millivolt reading that you're getting on the instrument, and then you will get a true value for the hot junction temperature that you want to measure. So it sounds a little bit complicated when you're first new to this, but after you've been working with them for a while, it becomes second nature to you and you do get used to the method. And what I will just do is swap over these connections so you can see that both units operate in the same manner. Take out that there. So we'll plug our thermocouple from the dry well in, and you can see that that's now reading 5.86, 5.87 volts. So very close. Again, this unit is not really that stable, so it's in the ballpark figure of what this unit was. And if I plug this one in, which should be the ambient, you can see that he's reading 0.03 millivolts. So it shows you that both these units are operating in the same manner. We can turn on our LB02 here. You can go between measure and source on the millivolts here on this one, and you can see we're at 0 millivolts on that one as well for measurement function. And if I just pop this out here and get them out and put them in there, and you can really see we're down to 5.79 millivolts. It's a minus because we've put it in the wrong way around. 5.80, so again that's working exactly the same as these other two units. Okay, so with this little experiment, what we're trying to do is force these cold junction down to 0 degrees C. If you remember, I'm saying that what the instrument's actually measuring is the difference between these two junctions here, and this one is ambient. If you look on the reference tables, if you get the reference junction, the cold junction, down to 0 degrees C, then it should put out 0 millivolts, in which case the should get then a true reading of the thermocouple voltage. Now how well I can do this, I'm not 100% sure. It might work, it might not. As you can see, it's actually already rising and going up there as we cool that down. And of course, how well I can actually keep this at 0, especially without shorting out the junction completely as well. But again, there it's climbing up, 6.2 volts there. So we should be heading for 6.540 millivolts, is what we will get, hopefully. So it's been a wee while, and we finally got there. I'm not sure how accurate this little thermometer is that I've put into this ice bath. That's showing 2.5 degrees C. We are 6.54 millivolts. So it's not worked particularly brilliantly, but you get the general idea. If I take this junction down to 0 volts, the cold junction temperature, 0 millivolts come out. So you then get a true reading of the millivolts of your hot junction there, or the temperature you're actually trying to measure. Now, this is obviously a bit of a lash together, believe it or not. There is specific equipment that's available to make these measurements that has an ice chamber within it, and it does freeze this junction down and holds it there at 0, and then you can characterize a thermocouple properly. This is one of those instruments from Omega. It sells for over $4,000, so yeah, not a piece of cheap equipment, certainly not in the price category of these things, and obviously totally impractical for taking out on site, which is where you would use these. But the object of this experiment was just to show you the principle of how that worked. So we swap back over to our Fnirsi unit here, and that's showing again the same, 6.58 millivolts, 6.57, so pretty good standard for all of them. We'll do the MR9270S as well, and just show you they should all read the same. Down here, 6.53 millivolts, so yeah, all working well and good. Now obviously, as I said, this isn't very practical for out on site, so what these units have is temperature capability built in with them, and what I need to do is go to Thermocouple, which is that one there, and we are already set up on an E, so we need to change this to a K. We edit that. So now we've set that up, you can see it's 179 degrees C, which is incorrect. That's because this unit, when set to temperature, as do all the other units, try and compensate for a cold junction temperature that will be at ambient. So if we go back to our settings, you can see we are on cold junction temperature, and we have to make sure that this is set to custom down the bottom here, and then we can edit that, and we can take them down to 0. We can OK that, we can exit, and you can see now I'm at 159 degrees C, matching the 160 within the tolerances there, no problems. Okay, we're going to test out the first temperature transmitter. That's this one at the back here, the little LKM101. This is the least accurate transmitter I've got. It's got a 1% accuracy on this. We can test this with either the millivolts or the thermocouple. Just to make life easier, I'm going to set this up for a K-type thermocouple using the LB02 here, and that's on measure, so we need to change that to transmit or source, and we're going to set this SG-004A here up to power and measure the loop current, because this is a loop powered transmitter, and we do that by going to the out function and setting that up as a 24 volt function there. And we come back, and then when we hit the enter, it energizes it. We get our power supply to our transmitter, and you can see we are measuring 3.95 milliamps for a 0 degrees C output. Tolerance on this at 0 degrees C will be between 3.746 and 4.254 milliamps. So you can see that's totally within spec. This is 0 to 1000, so we'll go to the mid-range, 500. We go up here, this is the problem with the LB02. Now we're into 3 digits. I can hit the step button, but I can only get between the units and the decimals. I can't get to the hundreds, so we have to ramp this up in tens. It's not too bad. Only when you've been doing it a lot, this starts to become a little bit more annoying. We've got 11.88 milliamps there, and we should be between 11.738 and 12.262, so that too is good. And we go finally all the way up to 1000. 1000 there, and obviously that should be 20 milliamp and should be between 19.73 and 20.27, and we are 19.82, so that's all within spec. And I put this table up here now. This is the measurements made with always this one powering the loop and reading the current, and then either the LB02, the SG-004 or the MR9270S sourcing the thermocouple, and they are all measuring totally within specification. No problems using this kind of setup for a 1% transmitter. Okay, this is our second transmitter. This is from lab facility. This is actually a 0 to 600 degrees C and is a 0.2% tolerance, so considerably greater tolerance than the first unit that we tested. In this instance, I'm using the SG-004A. Again, we're sticking to thermocouple functionality using the temperature rather than millivolts. And on this one, the output should be between 3.95 and 4.05, and you can see we're at 3.98, which is all good. For the SG-004A, slightly easier to adjust the temperatures on this. You just scale over to whichever digit you want and use the up and down arrow keys. So mid-range, which is 300. At 300 degrees C, it should be between 11.94 and 12.06, and you can see we're not. We're 11.83. We're out. And if I go up to 600, we are smack on 20. We're allowed between 19.93 and 20.07, which is within specification, obviously. But this centre reading here can't get in spec with this setup. I have tried with the other units again, and it produces the same kind of response, that you're in spec down at the bottom end and out of spec in the middle, and then back in spec again at the upper end. I have even had this hooked up to my reference kit, which is obviously way more accurate, and I get the same response again in specification at the bottom and top, but in the middle region it's out of specification. So whilst you struggle to use this to actually measure the accuracy, it will tell you if there is a fault on this transmitter, as there appears to be with this. I did actually go and get a second transmitter from a lab facility to see if that one performed the same, and it does. So I'm not 100% sure why, but I can't get these transmitters from lab facility to operate within their specification, yet I can get other units. So I don't think it's anything that I'm doing. I might be wrong, but I've played and just can't get this to read within specification, unfortunately. So this is our final transmitter. This is from RS Pro, and this is a 0.1% 0 to 1000 degrees C transmitter, so it's the most accurate one that I've got. This time we're using the MR9270S and the SG-004A again to measure the current. Again, loop powered, so test setup is the same on all of these transmitters. For our 0 degrees C we are putting in, we are reading 3.92, but we are out of spec. We should be reading somewhere between 3.971 and 4.029, so that's not much good at all really. This operates in a similar manner to the SG-004A, fairly easy to set this up. You can just move the arrows around and then move the up and down to set this up. 1000 is the maximum, which is 19.96 we are showing, and we should be between 19.95 and 20.05, so we are just within specification on that one, although it does tend to bounce around a little bit. I didn't do mid-range, did I? So let's take it back to 0, go across and go up to 500, and 500 we should be between 11.96 and 12.037, and yeah, we're 11.93. Again, it does bounce around a little bit, but we are out of spec again, and unfortunately this unit, as it is, you just can't make the tolerance for this transmitter. I'm just going to replace this with our HT8051, which obviously has a higher specification for measuring. Polarity the right way around. Not sure how well we can see that okay. So mid-range now, we are 12.007, which is obviously within specification. We can go all the way back down to 0, and we are 4.029. Yeah, it's difficult to read it. This is the problem I'm having with this unit. It's bouncing around an awful lot, so it's not the best, but it's very close to it. Let's go up to 1000, and we are 20.013 there, and we should be 20.028 maximum, so that's within spec as well. So source capability wise, all of these three units working with the HT8051, I can get in spec readings. Working with the SG-003A there is out of spec, which is to be expected. This unit here is a low specification. It's cheap, isn't it? You know, it's asking an awful lot of it to be able to measure the capability or the accuracy of a 0.1% transmitter. Just can't do it. Whereas instruments like this can, although as I say, it is bouncing around a wee little bit. So this will be our final way of testing out one of these transmitters here. I'm using the MR9270S. I could also use the SG-004A because both of these units can source and measure at the same time. The LB02, only having 2 jacks, can only source or measure. It can't do both, so this can't do this test. What we're doing here, we have an external 24-volt supply, so if we're out in the field, this transmitter was in the field, this is what you'd have coming out. That comes into your transmitter. You then interrupt the transmitter leg going back to your system with the MR9270S, so it comes in here, and then the negative input goes back out and goes back to my supply, or what would be the system, and then my millivolt output is just set up as per the previous tests. So what I need to do is change this input here, and we need that up to milliamps, which is number 1 up there. So that is now measuring milliamps. You can see we're reading 3.94. We haven't turned our output on, which is why it's bouncing around. Turn our output on. It should drop down to 4.0. 3.994. So we are now within spec. 3.994. It should be 3.971. So that is within specification. We can go up to our 500. And again, we are 500. We are looking for between 11.963 and 12.037. We've got 11.992, nice and accurate, all within spec. And finally go up to your 1000 there. And obviously it should be 20 milliamps, between 19.955 and 20.045. We actually smack on 20. 20.001, we can let it away with that one, can't we? So yeah, using this unit, as long as you've got the external 24 volt supply, or you rig one up, you can use this unit and the SG-004A to source and measure thermocouple, test out the transmitter completely just with the one unit, and that works, and I can get it in spec, no problems. It works with all these other transmitters other than the lab facility that I can't get into specification anyway, but the principle still works. You can test it in the same manner. Yeah, unfortunately though, as with the RTD, when I tested out the RTD transmitters, I can't get these units to source the 24 volts, measure the current, and then source the thermocouple voltage. It just won't do it. You end up with erratic readings. You do need that 24 volt supply, that external 24 volt supply, to do it in this manner, which is a bit of a shame, but at least you can do it with just the one unit should you want to. So at the beginning of the video I said we had an issue with the T thermocouple function on this SG-004A. One of the things you can do with these little calibrators is, if you have a multimeter that's got temperature functionality on it, this here has K-type functionality on the key site here. I'll set the LB02 up to K-type, and you can just wire this in and just dial in the temperatures you want, and you can verify the temperature readings all the way up to maximum temperature that you can get on these units. 10, you keep going. So this is a good way to test the temperature functionality out on a multimeter, and this is how I found out the issue with the T thermocouple on this SG-003A. You can see hopefully on here, if I turn it back on, the MTR105 does have a T thermocouple. T thermocouples are more accurate than the K types, so presumably that's why they've gone for it. Move them over here so hopefully you can see, get the glare off it. I've set this up to T type thermocouple here. We're on 300 degrees C, we match 299 on the meter, that's all good. If we start to go down, 290, 289, and again 280, 279, 270, 269, and now I can't go any lower than that. It just will not go. So not quite sure why it's done that. As I say, I think there's an issue with the firmware. Just to prove the point, we'll go into the LB02 here. We'll need to page him across to get to the T-type. There's the T-type there. You're switched off. We're on 0 and minus 1.5, so you can see we're on 0 degrees C. This always resets, so when you change the temperature it goes to 0, but we can go all the way up 60, 58.3, 100, 98.5. So you can see this one's working fine, giving the full range for the T thermocouple. Exactly the same as the MR9270S, that does give the full range for the T-type thermocouple as well. It's just an issue with that SG-004A there. So there you have it. That's done some testing with some thermocouples and temperature transmitters using the LB02, the SG-004A and the MR9270S there. Pretty acceptable set of results. Obviously these two units do have a little bit of an advantage over the LB02 with being able to source and measure at the same time, so you can test out the functionality if you have the 24 volt supply available to it. Accuracy wise, probably plummet for the MR9270S really. That seems to give me the best functionality and the best set of results that I've had with doing this testing. The LB02 is good, but obviously it's limited with just its one set of jacks. The SG-004A, it's okay, it will do the job for you. I do find this erratic. The readings they're not as stable as they are on these other two units. And I did have a bit of an issue with the cold junction compensation on this unit here. It doesn't seem to be as accurate as these other two and seems to drift away. Obviously you can force it and set it up for whatever you like if you can measure it differently, or you can move to millivolt functionality for both of these units, and then really these units are fairly comparable really when you're using millivolts as opposed to the thermocouple functionality built into them. But that's the same for a lot of calibrators. You will generally get better accuracy using the millivolt functionality if you can measure the ambient temperature accurately enough. These ones drift more when you're using the temperature functionality because the internal cold junction temperature compensation is probably the least accurate part of it. But obviously it comes into the equation because he's using that for the calculation. But that'll be the end for this video, a bit of a long one unfortunately. I hope you found it useful. Thanks very much for watching, and I'll see you again in the next one.